So this is quantum dots and noise-resistant quantum key distribution systems. Our members is Samuel, Prahlad, Praneel, and Aditya, and Elaine and Sophia, but they couldn't join us today. So what are quantum dots? Initially discovered in 1980, quantum dots are semiconducting nanoscale particles measuring between 2 and 10 nanometers or 10 to 50 atoms in diameter. Some materials of which they can be composed are cadmium selenide, lead sulfide, indium phosphide, zinc sulfide, copper indium sulfide, zinc sulfide, indium gallium arsenide, silicon, germanium, and carbon. They exhibit unique electronic characteristics that range from those of larger semiconducting materials and individual molecules. This is due to their exceptionally high surface to volume ratios, which manifests in fluorescence. Quantum dots generate colors based on their particular size. This is made possible by the semiconducting crystal's radii falling short of the exciton-Bohr radius, which is the average distance between an electron in the conduction band and the hole it creates in the valence band. As pointed out by Pauli's exclusion principle, this leads to the quantization of the energy levels. So due to the discrete energy levels of quantum dots, they are more akin to atoms than bulk materials. As the crystal size reduces, the energy gap between the highest valence band and the lowest conduction band widens. Quantum dots can be classified based on their structure and composition into core type, core shell, and alloyed quantum dots. Overall, quantum dots have various applications due to the various benefits their distinctive properties offer. These include their optical abilities to emit pure, bright colors, extended lifetimes, high efficiency, and having a high extinction coefficient. Additionally, quantum dots being zero-dimensional entities exhibit a more defined density of states compared to structures with higher dimensions. An electron's travel distance is reduced compared to larger particles, thereby enabling electronic devices to function at higher speeds. Quantum dots also possess size-tunable emission, high photostability, and narrow emission spectra. Quantum dots can be utilized in quantum computing due to their ability to functional similarity to transistors. Information is not stored using transistors as in classical computers, but rather through individual atoms, ions, electrons, or photons that are entangled to form quantum bits, known as qubits. These quantum scale units can hold multiple values simultaneously and process various tasks concurrently. Managing individual atoms and similar entities in this manner can be challenging, but utilizing quantum dots on a larger scale would simplify the process significantly. What is QKD? QKD systems have the potential to revolutionize the way we communicate and protect our data. The development of new and more secure QKD systems will significantly impact various industries, including telecommunications, finance, and national security. Typical public-private key cryptography is a method along with a protocol that allows one person to transmit encrypted data to another person for them to read. A private key encrypts the data. If you want to make it clear that the data comes from you, use a public key to send it out into the world, and then it can be decrypted. However, if you want to designate data for only one person, encrypt it with a private key, then your public key, and the receiver will decrypt it with a private key and his public key. Public-private key cryptography has use cases in various realms other than sending confidential information. For example, you can sign a document with your private key, and someone who has your public key can determine that you are the individual who signed the document. Quantum key distributions, or QKD, is a cryptographic protocol that allows two parties to share a secret key over an insecure channel. However, QKD is based on the principles of quantum mechanics, harvesting the benefit of being unbreakable by current technology. A QKD system uses quantum entanglement and superposition of qubits to ensure a safe transfer of encryption keys for later communication. Existing platforms implement quantum-resistant algorithms, which rely on mathematical complexity to ensure security. These algorithms, integrated into cryptographic protocols, play a crucial role in guaranteeing the confidentiality, integrity, and authentication of transmissions. They are designed to withstand potential threats from future quantum computers. It is also designed to be able to detect the presence of an eavesdropper. So in an open data channel, you cannot detect an eavesdropper. But in QKD, an eavesdropper must disturb wavelengths, which can easily be detected. Applications of QKD. So these include secure communication, financial services, government and defense, healthcare and medical research, critical infrastructure protection, and quantum internet, which is a network of quantum computers that will, in the future, someday send, compute, and receive information encoded in quantum states. Description of project. So this research project is meant to analyze ways quantum dots can be better integrated into quantum key distribution networks to counter interference impacts such as noise and detect the presence of eavesdroppers. So in opposition to typical private key encryption, QKD encryption uses quantum effects to guarantee the security of a private key over an open channel. However, currently, the presence and magnitude of noise or interference from the environment, such as heat, electronic noise, etc., degrades the security of QKD systems and makes it easier for eavesdropper to potentially access the key. Through the results gathered through advanced simulations, which ran on a high-performance computing cluster simulating QKD systems, new insight into how unique quantum dot properties can improve noise resistance emerged from the data. These findings suggested potential developments in security and privacy, which sprouted from the implementation of newer quantum communication protocols and channels. So in addition, this research could lead to more robust QKD systems that can be utilized in sectors where privacy is important, such as telecommunications and national security.
We have three different models, the quantum key distribution model, the quantum dots model, and the noise model, which models spin and charge noise. We are currently using these models in tandem in the integration process. More on that later. Limitations of current QKD systems. Quantum dots are promising candidates for noise-resistant QKD systems. Their unique optical and electronic properties make them well-suited for QKD. For example, QDs can be used to generate and detect single photons, which are basic unit of information in QKD. They can also be used to create entangled photons, which are used to establish a shared secret key between the two parties. However, QKD systems are still susceptible to noise. Noise can be caused by a variety of factors, such as environmental factors, electronic noise, and malicious attacks. Noise can degrade the security of a QKD system and can make it easier for an attacker to eavesdrop on the secret key. Single photon emitting lasers, diodes, and photodiode detectors, which most QKD systems use, are sensitive to noise, which refers to multiple factors that can affect the accuracy of the calculations a quantum computer performs, including environmental factors such as temperature and background radiation. QKD model. The first step to our project was to implement the standard QKD with code using the IBM Qiskit Python library. We modeled individual photons sent between the two parties as qubits, and we were able to model photon superposition and entanglement using the Hadamard and C0 quantum gates to ensure that our basic quantum key distribution scheme functions. We simulated the scheme with and without the presence of an eavesdropper. We were able to successfully determine the presence of an eavesdropper using the simulation, confirming the validity of our simulation.
Next is the quantum dots model. Using a function we named variational form, we constructed a quantum circuit representing two quantum dots in the quantum key distribution system. This circuit, using rotation gates and parameterized by params, allows us to explore different configurations. The chosen number of qubits corresponds to the quantum dots in our simulated QKD scenario. So you can envision the quantum circuit as a structured environment governed by the rotation gates and the parameters as discussed earlier. These parameters introduce a dynamic element into the circuit, enabling various configurations for our quantum dots. Moreover, the explicitly specified number of qubits in this quantum circuit aligns precisely with the quantum dots in our simulated QKD scenario.
Admin, please mute MG. Admin, please mute MG.
There, Emma.
Thank you. Okay, Prahlad, go ahead.
Thank you. So the quantum circuit, meticulously directed by the variational form function, serves as a computational canvas for crafting the quantum representation of our simulated quantum dots. At each instance of a rotation gate and adjustment of parameters, we unveil a multitude of configurations. So moving on, there's a poly dictionary that holds poly operators acting as observables for the quantum dot interactions in the QKD system. These operators define the characteristics of quantum dots. The Hamiltonian, a summed up of poly-sum up instances, provides a mathematical expression encapsulating the quantum dot system's features. So what is this Hamiltonian, right? I mean, or the operators in the Hamiltonian. So these operators, in simple terms, they're like detectives. They observe and like record different aspects of how quantum dots behave. So spin, orientation, and other quantum features are their specialties. So the Pauli dictionary we use essentially compiles these observations together and gives us a manual like to interpret the intricacies of quantum dot behavior. So the Hamiltonian, which is a sum of these operators, right? Like imagine it as a equation that sums up all these characteristics we extracted from the Pauli dictionary. So the equation becomes our roadmap, and it's a mathematical representation for the quantum dot system's features. The Hamiltonian is the key to understanding the impact of different quantum dot setups on the stability and reliability of the QKD system. So it's basically like the bridge between the observations we made with the Pauli operators and the practical implications for a quantum communication system. Next slide. Now let's see how quantum dots behave within the QKD system. Our tool of choice for this exploration is something called VQE, the Variational Quantum Eigensolver algorithm. Think of VQE as a precise investigator on a mission to unveil the ground state energy of our quantum system. Kind of a sort of cosmic detective probing the stability of the quantum dots within the QKD setup. The method involves adjusting variational parameters, essentially tweaking the conditions to simulate different scenarios. It's similar to orchestrating controlled experiments to observe how quantum dots respond within the QKD framework. As we manipulate these variational parameters, VQE takes charge, and it navigates through the quantum landscape to pinpoint the optimal condition. But what does it bring back? It brings back a set of optimal parameters and the ground state energy. These optimal parameters, they encapsulate the specific rotations and maneuvers that guide our quantum dots in stable configurations within the QKD system. It's related to decoding the language of quantum dots to understand the precise combination that ensures stability. The ground state energy in this context acts as a weather glass for this stability. A lower energy level signifies a more stable arrangement of quantum dots, vice versa, but the lower energy level indicates resilience against external disturbances. It's a quantitative measure of how well our quantum dots maintain composure within the QKD system. So why does this matter, right? So as discussed before, the optimal parameters we get from VQE guides the actions of the quantum dots. And these parameters represented as the rotations and manipulations and in the quantum circuit, they set up these stable arrangements, and watching how these parameters change gives us insights into preferred states and configurations that make the QKD system more stable, resilient, and easier to optimize quantum dot performance.
Noise model. The purpose of a noise model is to explore sources of noise such as charge noise, environmental noise, background radiation, etc., in order to identify how they affect QKD systems. For the purpose of our research, we used the Qiskit AER library to create a model that explores spin and charge noise. With our noise model, we also aim to figure out potential strategies to mitigate these noises. In physics, spin refers to the angular momentum, quantity, associated with the subatomic particles or nuclei, measured in the units of Dirac H, also known as h-bar, which is the Planck constant, divided by 2 pi. The spin values of electrons, neutrons, and protons are multiplied by half, while pions have a spin value of 0. The total angular momentum of more complex nuclei is the combined result of the orbital angular momenta and the intrinsic spins of the constituent nucleons. Nuclei with an even mass number exhibit integer spin multiples, whereas those with an odd mass number have half integer spin multiples. Ground states of nuclei with an even number of neutrons and protons always possess a spin value of 0. There are random fluctuations in the spin orientation of electrons in quantum dot. In the context of quantum computing, quantum dots are used as potential qubits, and so these fluctuations can affect the reliability of quantum operations. Pauli errors are common errors in quantum computing and can arise from various sources, such as imperfect gates, environmental interactions, or other noise mechanisms. This is a way in which spin noise is represented in the model. Notably, the error rate associated with spin noise is tied to temperature variation. Next slide. In our noise model, we also represented charge noise. Charge noise is fluctuation in the amount of electrons in a quantum dot. These fluctuations often cause errors in quantum operations. In our noise model, the charge noise is represented through a stochastic matrix. We calculate the error rate or amount of error based on the standard deviation of the charge from the mean. We also represent the effect of magnetic field on the quantum dot in our model. We represent the magnetic field with a Hamiltonian. A Hamiltonian is a mathematical operator that represents the total energy of a physical system. Our Hamiltonian is a time dependent and based on the cosine function to represent oscillation in energy. Next slide.
Here are some areas of current research related to quantum dots and noise-resistant QKD systems. So starting off with single photon sources, quantum dots can act as efficient and high-quality photon sources, which are crucial for QKD systems. So researchers are exploring different types of quantum dots, such as self-assembled quantum dots and semiconductor nanowire quantum dots to develop robust single photon emitters with high photon purity and indistinguishability. Next, quantum dot qubits. So quantum dots can also serve as qubits, the basic building blocks of quantum computers. Researchers are investigating the integration of qubits based on quantum dots into QKD systems to enhance the security and efficiency of key distribution. So this research aims to exploit the unique properties of quantum dots, such as long coherence times and ease of control, to improve the performance of QKD protocols. Next, noise-resistant protocols. Quantum dots offer the potential to mitigate various noise sources that can compromise the security of QKD systems. For instance, researchers are developing protocols that can tolerate high levels of noise and loss, such as the use of quantum error correction codes and decoy state protocols. These approaches aim to make QKD systems based on quantum dots more resilient to practical limitations and environmental disturbances. But finally, integration with other technologies. So to enable practical deployment of QKD systems, researchers are working on integrating quantum dots with other technologies. So for example, quantum dots can be integrated with photonic integrated circuits, allowing for miniaturization and scalability of QKD systems. So integration with on-chip photon detectors and quantum memories is also being explored to create compact and efficient QKD platforms. Integrated models diagram. So in our integrated quantum communication system, we start with the quantum dot source. So at this initial stage, we generate entangled photon pairs using quantum dots, which are semiconductor nanostructures with discrete energy levels. The quantum dots are precisely engineered to emit pairs of photons that are quantum mechanically entangled, meaning their quantum states are interconnected regardless of the distance separating them. We also defined a specific quantum dot parameters such as the energy level and the emission wavelength to ensure optimal performance and compatibility with the rest of the system. Next, these entangled photons move on to the photon emission phase. So here the photons are transmitted through a communication channel. So during this phase, quantum gates and encoding schemes are applied to encode the information onto the photons. So quantum gates are fundamental operations that manipulate the quantum states of the photons, enabling the encoding of secure information. This step is crucial as it prepares the photons for secure transmission over potentially insecure channels. As the photons travel through the communication channel, they encounter various forms of noise introduction. This stage accounts for the environmental noise that can affect the quantum states of the photons. So several factors contribute to this noise, including charge fluctuations within the material, interactions with phonons, which are quantized sound waves within the material, and other decoherence processes that can disrupt the quantum states. So these environmental factors can introduce errors and reduce the fidelity of the transmitted information. But despite these challenges, the photons eventually reach the receiver measurement stage. So here, specialized detectors encode the quantum states of the incoming photons. So this measurement is critical as it allows the receiver to decode the information encoded in the photon states during transmission. The accuracy and efficiency of these measurements are extremely vital for the integrity of the communication. But following the measurement, the system moves to the key generation phase. So during this stage, the shared secret key is established between the communicating parties. The key generation process involves calculating the secret key rate, which is a measure of how many secure bits can be extracted per transmission, and the fidelity, which indicates the quality of the transmitted key. So high fidelity is essential to ensure that the key is free from errors and eavesdropping attempts. To further enhance the security and reliability of the communication, we implement error correction and privacy amplification. So error correction involves applying codes that can detect and correct errors that may have occurred during transmission due to noise. Privacy amplification techniques are used to reduce any partial information an eavesdropper might have gained, thus ensuring the key remains confidential. So these techniques are extremely crucial for maintaining the security of the quantum key distribution. Finally, the process concludes at the end stage. So by integrating quantum dot technology for generating entangled photons, quantum key distribution protocols, and effective noise management and correction techniques, a secure and reliable quantum communication is established.
So as of now, what we've done is we've already integrated the QKD model and the noise model together. So that part of the integration is complete. We still have to, and that part of the integration was relatively simple because the Qiskit library actually has an inbuilt basically area where you can input a noise model. So that part of the integration was relatively simple. We just had to move the noise model into the QKD model essentially. The QKD and QD integration is slightly more difficult because there's no direct spot to put it in. So we have to change the code of both of the models in order to fit them together correctly. But we're currently working on that and we should be done in a couple weeks. And then we're also concurrently writing the paper. And then once we get the results from the QKD and QD integration, we'll input them into the paper and we will be done with our project. Next slide. Sorry. So yeah, kind of like I said, we're currently working on integrating the QKD and QD models, and we're also working on finishing the research paper, and that's all we have for future work. These are our citations that we used, and thank you ASDRP and Dr. McMahon. Are there any questions?